Imagine an award-winning marvel of engineering, hailed as a model of dam safety, suddenly unleashing a catastrophic flood. The true story of the Taum Sauk Power Station reveals how a series of seemingly minor oversights could lead to a disaster that reshaped an entire industry. Early in the morning of December 14, 2005, pumps were nearly finished filling the upper reservoir at the Taum Sauk Power Station, marking the end of the daily cycle. Water rose to the top of the rockfill embankment, reaching the concrete parapet wall that ran along the top of the dam. But the water didn't stop. One of the two pumps shut off, but the other kept running. Soon, water was lapping over the wall. Within minutes, those splashes turned into a steady stream cascading over the parapet, pouring against the embankment on the other side. The rockfill eroded slowly at first, but the hole grew deeper and wider. The pump finally shut off, but it was too late. The footing of the parapet wall had already been undermined. The wall tipped over, and a massive surge of water was unleashed down the mountainside, directly toward a state park. This incident immediately placed the facility, considered a model of modern engineering, under intense scrutiny. What the investigations found would profoundly change the field of dam safety on Infrastructure Watch. When it was built in the 1960s, the Taum Sauk pumped storage plant was unlike any other power plant in the world, at least in terms of size. Located south of St. Louis in the Ozark Mountains, it was designed to meet a very specific need. Taum Sauk was one of the largest pumped storage facilities of its time. Built by Union Electric, which eventually merged with Ameren, the entire plant functions essentially as a battery. It is, in fact, a net consumer of electricity, which normally isn't a good characteristic for a power plant. However, managing the power grid isn't solely about the quantity of electricity produced, but also about the timing of its production. Large coal plants in the Missouri area could generate vast amounts of power, but they struggled to adjust their output to accommodate fluctuating daily demands. Union Electric therefore proposed a clever solution, common today but innovative for its era, constructing two reservoirs. One was located low on the east fork of the Black River, and another near the top of Prophet's Mountain, Missouri's sixth highest peak. Between them, a hydroelectric plant with two reversible turbines was installed. When electrical demands are low, typically overnight, instead of reducing the output of thermal power plants, that surplus energy can be used to pump water from the lower to the upper reservoir. Then, when demand spikes during the day, all that stored potential energy, created from cheap electricity, can be harvested and returned to the grid by reversing the system to generate hydropower. Naturally, not all the energy put in is recovered. Some water evaporates or leaks, and there are inherent energy losses during pumping and generation. However, with an overall efficiency of around 70%, this system was more than sufficient to justify the enormous cost of building and operating two reservoirs and a power plant that generates no net electricity of its own. The most striking feature of the entire facility is the upper reservoir. It presents an unusual sight, a circular dam, sometimes referred to as a ring dike or ring levee, perched atop a mountain. This configuration is not typically an efficient way to build a dam. Dams are usually constructed across valleys, allowing the natural topography to form the sides and back of the reservoir. With an off-channel reservoir, like Taum Sauk, the dam must be built all the way around, significantly increasing costs and engineering complexity. Yet, there are no valleys at mountain summits, and that height difference is an essential component of a pumped storage facility. The power available from falling water is straightforward to calculate. It's the product of gravitational acceleration, fluid density, volumetric flow rate, and the difference in height, known as head. Only two of these factors can realistically be changed. Thus, for a specific power output over a given duration, height can be traded for flow. The greater the height difference between the two reservoirs in a pumped storage facility, the less water needs to be moved, which reduces the size of all the associated infrastructure and, consequently, saves costs. The mountains in southeast Missouri provided an ideal location for the project, creating a height difference of about 230 meters between the upper and lower reservoirs. The facility itself is named after Taum Sauk, Missouri's highest mountain, which was the original proposed site for the upper reservoir. However, due to significant public opposition, the project was relocated to a slightly lower, nearby peak. Engineers encountered challenging geological conditions during construction, necessitating a realignment of the dam to avoid weak areas, which resulted in its unique kidney bean shape. The original dam was constructed as a rockfill embankment, essentially a large pile of rocks dumped around the reservoir's perimeter. Rockfill generally performs well as an embankment if a good source of material is readily available. It is inherently strong, requires minimal compaction, and settles less over time compared to soil fills. However, rock fill is not effective at retaining water due to the numerous spaces between the rocks. To address this, concrete panels were installed along the entire inside of the reservoir to ensure the embankment was watertight. A tunnel connected a Morning Glory inlet through the mountain to the generating plant. This inlet was positioned in a basin 6 meters below the reservoir's bottom to prevent vortex formation as the reservoir drained daily. The entire project was designed for remote operation, requiring no on-site technicians, an innovation for its time, but one of many decisions that would ultimately prove disastrous. For most of its operational life, the Taum Sauk Station ran for an average of approximately 100 days per year, primarily during the hot summer months when electricity demands exhibited greater variability between night and day. The deregulation of electric power markets in the 1990s created opportunities to sell power to other utilities. Consequently, the operational days increased from 100 to 300 per year, meaning the upper reservoir cycled up and down, often twice daily, almost every day of the year. This intensified operation began to cause problems. The upper reservoir had experienced leaks virtually since it commenced operation in the 1960s. Several projects were undertaken throughout its lifespan to mitigate this issue, but the increased cycles of filling and draining only exacerbated the situation. At one point, small ponds were even constructed alongside the reservoir to capture some of the leakage and pump it back inside. In the autumn of 2004, Ameren decided to implement a major solution, spending over $2 million to install a geomembrane liner covering the entire reservoir. While this largely resolved the leakage problem, it inadvertently created several new issues. Approximately a year later, in September 2005, the Institute of Electrical and Electronics Engineers, IEEE, declared the plant an engineering milestone for its innovations in electrical infrastructure. The day before the ceremony, some participants toured the upper reservoir and observed water pouring over the parapet wall on one side of the dam. Operators quickly switched from pumping to generation mode to lower the water level. They attributed the overtopping to high winds from a remnant tropical storm, but as a precaution, they hired a dive inspection team to check the level sensors. What the team discovered was concerning. When the geomembrane liner was installed, there was a valid concern that any penetrations might cause future leaks. However, the reservoir required level sensors for the remote control system. Therefore, instead of mounting these sensors directly to the concrete through the liner along their full length, engineers devised an alternative method. Two cables were run between anchors at the top and bottom of the embankment slope, and the conduits for the sensors were attached to these cables, minimizing the number of necessary penetrations. Unfortunately, this mounting system was underdesigned. The conduits were buoyant and also subjected to strong currents as the reservoir filled and emptied daily. Sometime after the spring of 2004, they had become dislodged and deflected, causing the sensors inside to provide readings that were lower than the actual water level. Based on these findings, operators decided to reprogram the control system to subtract 600 mm from the upper set point on the pumps. The original design mandated 600 mm of freeboard between the top of the wall and the maximum water surface. They believed that doubling this distance would be sufficient to prevent further issues until permanent repairs could be undertaken during the annual maintenance period when the reservoir was drained. Tragically, they would never get that chance. Less than 3 months after the initial observation of the reservoir overflowing, on December 14, it happened again, this time in the early dawn with no one present to notice. Once the parapet wall collapsed, the water rapidly eroded through the dam, releasing approximately 6 billion liters of water down the steep mountainside directly toward Johnson's shut-in state park, stripping away trees and rocks in its surge. By sheer luck, the failure occurred in winter when the park was almost empty. However, the park superintendent, his wife, and their 3 children, one only 7 months old, were swept away when the water demolished their house. Incredibly, the entire family survived the event, though they suffered injuries and hypothermia. The massive wave of water ultimately flowed into the lower reservoir, where it would have naturally gone later that day, thus preventing major downstream impacts. The Federal Energy Regulatory Commission thoroughly investigated the event, and its conclusions were startling. Like most incidents of this nature, a series of seemingly minor oversights, which individually would not have led to disaster, combined to cause hundreds of millions of dollars in damage, in addition to the profound impact on the family. The first issue concerned the embankment itself. The rockfill material, from which it was supposed to be constructed, contained significantly more soil than the designing engineers had intended. This resulted in greater settlement of the embankment over time. Furthermore, unsound soil areas in the embankment's foundation were not properly cleared, exacerbating the settlement. From its construction to its failure, some sections of the parapet wall had settled a full 600 mm lower than their original design elevation. This settlement was not accounted for when the level sensors were replaced after the lining project in 2004. With the sensors dislodged and free to move, the logic controllers had no accurate means of determining the actual water elevation in the reservoir. Failsafe probes were installed on the parapet wall as a backup, designed to automatically shut off the pumps if the water level became too high. However, these probes were positioned at an elevation that was actually higher than the top of the settled sections of the embankment wall. If the water reached these sensors, it had already begun overtopping parts of the wall. To make matters worse, they were incorrectly programmed to require both sensors to be activated before the pumps would shut off. The initial site visit in September, when water was observed running over the wall, did not trigger these failsafe sensors, yet no one thought to inspect them. Rather than accurately verifying critical elevations like the top of the wall and all sensor levels, the operators simply decided to add a few feet of margin and postpone a permanent fix. It would have been remarkably simple to have someone on site during the final minutes of the reservoir's daily filling to cross-verify the electronic measurements, or even to install a closed-circuit camera, especially after the glaring red flag of the earlier overtopping. Yet, no one realized the extent of the problem. Furthermore, the owner had not notified the regulator the first time the overtopping occurred, meaning there was no external oversight of Amren's response. Perhaps the most significant error of all occurred long before the facility was ever built: the design lacked a spillway. As an off-channel reservoir, water could only enter in 2 ways: rainfall or being pumped in. With ample freeboard designed to accommodate rainstorms and the redundancies built into the control system, the original designers never anticipated a need for a mechanism to safely release excess water. Unfortunately, when safety relies on complex systems, the probability of things going wrong increases significantly. Such events are sometimes referred to as normal accidents, a term coined by Charles Perrow. The concept suggests that when systems are complex, and particularly when safety measures themselves add to a project's complexity, failures become more likely, even expected. In essence, failure becomes normal. In contrast to an intricate industrial control system, a spillway is remarkably simple. Once water reaches its crest, it simply flows out. While not entirely foolproof, as several spillway failures have occurred, there are far fewer ways for a basic spillway to malfunction. The Federal Energy Regulatory Commission, FERC, fined the owner $15 million for the failure, the largest penalty they had ever issued. $5 million of this fine was allocated to a fund for improving the area around the project, though some recent reports have alleged mismanagement of these funds. The state of Missouri also filed a lawsuit, reaching a $177 million settlement, much of which was directed towards restoration efforts at the state park, which held a reopening ceremony in 2010. Concurrently with the renovation of Johnson's shut-in state park, crews were rebuilding the upper reservoir at Taum Sauk. To circumvent a lengthy relicensing process, the new dam was constructed on the same alignment and to the same dimensions as the original project. Instead of attempting to repair the flawed rockfill embankment, Ameren and their consultants opted for an innovative design. The new dam was built using roller-compacted concrete, a dry concrete mix handled with earth-moving equipment and compacted into place using rollers. This new design effectively addressed both the settlement and leakage issues that plagued the original structure, while also utilizing material from the original embankment. The existing rockfill was crushed and processed into aggregate for the new concrete, reducing the amount of material that needed to be transported to the remote site. Crucially, this time, a spillway was included. The rebuilt structure now stands as the largest roller-compacted concrete dam in the United States. The plant reopened in 2010, was rededicated as an IEEE milestone, and the project received the U.S. Society on Dams Award of Excellence in the constructed project. The failure at Taum Sauk served as a profound wake-up call for the professional community. In the aftermath of the collapse, FERC, the regulatory body, implemented significant changes to its oversight of dam safety. They established a task force that issued a technical guidance document specifically addressing the unique challenges of pumped storage facilities, which was circulated to all owners. Furthermore, they updated regulations, requiring owners to establish an internal dam safety program and appoint a chief dam safety engineer responsible for its oversight, a role Ameren did not have at the time. The event prompted states as far as Hawaii to strengthen their dam safety programs. Most importantly, the failure unequivocally demonstrated the critical need for overflow spillways, even for off-channel reservoirs equipped with redundant control systems designed to prevent overfilling. For those tracking developments in the electrical grid, the importance of energy storage is undeniable. As intermittent power sources become a larger part of our energy portfolio, methods to balance mismatches in supply and demand are increasingly vital. Pumped storage has traditionally been the only large-scale, economically viable way to achieve this, but it inherently comes with trade-offs. Dams are among the riskiest structures humans build. While failures are infrequent, when they do occur, they typically result in severe consequences for people, property, and the environment. Because these failures are rare, the lessons learned often arrive slowly and tragically. However, as battery storage becomes cheaper and more widespread, it will be fascinating to observe how the economics of pumped storage evolve. By 2030, some predictions suggest the U.S. grid will incorporate over 400 gigawatt-hours of battery storage, equivalent to more than 100 Taum Sauks. We are at the cusp of major transformations in how energy is stored. These batteries present numerous technical differences in their grid interaction, and they come with their own environmental challenges and safety considerations. Yet, their risk profile is significantly different from constructing a massive reservoir atop a mountain. As energy infrastructure continues to evolve, these distinctions in risk will likely shape the future of power storage and its associated costs. The Taum Sauk incident underscores a recurring lesson: the immense, destructive power of water. Disasters, more than anything else, shape the field of engineering, serving as crucial teachers for future improvements. They highlight the importance of understanding how infrastructure interacts with natural forces, whether it helps or hinders during events like floods. The tragic failure at Taum Sauk, a facility once celebrated as an engineering milestone, starkly reminds us that vigilance, comprehensive design, and robust oversight are paramount when harnessing such powerful forces.